Today's lesson we're going to focus on standing waves in air columns. Okay, if you remember back from standing waves in strings, standing waves are simply an interference phenomenon. So what happens is you get a forced oscillation that interferes with a reflection, and that is going to create both areas of constructive and destructive interference. And like we saw on the standing waves in strings, you get points again where the interference, where you have constructive interference, you get those positive displacements or negative displacements that are called antinodes, and the places of node displacement known as nodes. If you kind of connect this to what interference means, interference is really using the superposition principle, a change in the amplitude. So what happens is you get a relative change in the intensity of sound. Okay, so this is can be produced on a spring, can also be produced in with air in certain pipes, and this is kind of the physics almost of piped instruments. All right, so what you get is a change in amplitude, and also, like we saw with strings, that it happens at specific frequencies. So you get these standing waves occurring with a change in amplitude, change in intensity, and a change in frequency, which also is a change in pitch. Alright, with standing waves in air columns, there's really two different types we're going to look at. First, we're going to look at closed end versus open ends, and really it should be simple to understand. A closed end is where, on your tube, closed end is something that is not open to the atmosphere. Okay, so the air particles within this tube are not free to move back and forth, not free to oscillate, right? As opposed to an open end, seen down here, where both ends of that tubed instrument are open to the environment. Alright, so the air particles are free to oscillate. So if we take that back to standing waves, what we talked about on strings, you have really two components of a standing wave. You have nodes and antinodes. Again, a node is a point of no displacement, an antinode is a place of maximum displacement. So first, looking at a closed tube, what you get, again, one end is not open to the environment. So the particles at that side are not allowed to oscillate. So what you get is a point of no displacement. And here the sound wave is going to travel through the tube, reflect off of this, bounce back, and then interfere with sound waves that are coming in. So here you get kind of the interference pattern of an incident wave meeting with a reflected wave. Again, here, thinking of the particles, remember sound waves, particles are going to oscillate parallel to the direction of motion. All right? So they're going to vibrate back and forth. A node here is where they're not going to oscillate back and forth. Here, these particles are open to the atmosphere, so the particles are free to move back and forth, and that's where you get that node and antinode. When looking at an open tube, you have on both sides here, you have both sides open to the atmosphere. Therefore, on both sides, you have particles that are free to oscillate back and forth in the direction of the wave. Okay, and if you haven't noticed so far, points where there's no displacement we call a node, points of maximum displacement we call an antinode. And notice when you have an antinode, okay, in between two antinodes there must be a node. Same thing between two nodes, there must be an antinode. It's going to kind of help us to understand the different standing waves in air columns. Alright, so remember that standing waves are basically a result of the interference between an incident wave and a reflected wave. So let's kind of look at what happens inside of these two types of air columns. The first one should be pretty easy. So when looking at a closed end, what happens is that you are basically sending a sound wave down to this closed end. So when the sound wave travels, again, the particles are oscillating back and forth in the direction of the wave. All right, and like I said before, the particles that are at kind of the bottom here at the closed end, these particles are not allowed to vibrate back and forth. The restriction of this closed end causes them to stay put. So what happens when this sound wave reaches this point here is obviously you get a part of the wave to reflect back. Right? So the particles are going to bounce off the walls and obviously then bounce back, causing these particles then to oscillate back and forth. So you obviously get a reflection here, and that should be pretty easy to see. Okay. With an open-end tube, it's a little more difficult. All right. So with an open-end tube, you get kind of the same thing. And what happens with a standing wave is you get the reflected wave interfering with the initial wave. Okay, so here again you have your wave traveling, let's say downward in this case. Your particles are oscillating back and forth. Same here, your particle at the end is free to move because it's now an open end, free to move back and forth. So why then, again, in order for a standing wave to occur, you need some of the sound wave reflected back into the medium. So some of the sound wave, when it gets to this open end, is going to reflect back. Okay, you get some of the wave coming in, like that, and then some of the wave bouncing back. So why does some of the sound bounce back into an open tube? By looking at this, kind of by how you may initially think, right, how is any of the sound, if this is open, what's it going to reflect off of, right? If we look at fixed versus free ends or different change in medium, all right, it's a pretty obvious to see how it's going to reflect back. But with an open end, how is that going to happen? Well, let's think about what we know already, all right? When you make a sound within this tube, these particles are moving, right? They have some velocity oscillating back and forth. That wave speed is going to travel through the medium. External to the tube, these particles are stationary, not really moving. Okay? You can see them as stationary. So think back to some of the earlier chapters, especially on fluids, is that when you have an increase in speed, what that results in is a decrease in pressure, right? So what happens is as these particles within the tube begin to oscillate back and forth, what happens is that their speed is beginning to increase, right? They're oscillating, meaning the overall pressure inside that tube is decreasing, right? And the pressure outside the tube out here, since these particles are not moving as fast here, or not oscillating, what you get is that outside the tube you get a higher pressure. Inside the tube you get a lower pressure. So what you get is almost like a wall right here where you have a low pressure versus a high pressure. Okay, so the difference in pressure almost creates, I guess I'll call it what's called like a pressure wall. Make up a term there. Okay, and this pressure wall is what causes some of the sound wave to reflect back. So that's how you get a standing wave inside an open columns. You get, because of the variation in pressure, you get some of that wave reflecting back and then would interfere with the incident wave. Alright, so let's go through the different standing waves we'll see first with a tube that's closed at one end. So remember, closed at one end, we're always going to get a node. So the first harmonic we're going to see, closed at one end, we're going to have one node, and then the other end that is open, we have an antinode. Right? So if you think about right now nodes and antinodes, right, there cannot be two nodes or two antinodes in a row. So anytime you have a node to an antinode, that represents, if you think about it, look at a picture, a quarter of a wavelength. So here, the first harmonic occurs with a closed at one end. Okay, first harmonic occurs when the wavelength is equal to 4 times the length. If you think here, one wavelength is like this, we're really getting only part of that wave. We're only getting a quarter of it. So the entire wavelength would be 4 times that length. Alright? Then the second one, when you have usually the second harmonic, what happens is you get a node, the antinode will go inside, and you should get on the other side another node. But if you look here, we are always going to have a node and an antinode at opposite ends. You can never have a node here at this open end. So what happens is what we get an antinode, we get another node, and then at the end you get an antinode. So really, instead of jumping to the second harmonic, we're actually jumping to the third. All right? If you think of what the second harmonic should look like, given this, you should have a node. You should basically be adding another node inside, right? So it would look like a half a wave, going from a quarter to a half. But we're jumping from a quarter, and not to a half, but we're jumping actually to 3/4 of a wave. All right? So we are jumping from the first to third harmonic. And this is an important thing about closed at one end, is that we are not going from first, second, third. We're going from first to third. And then jumping on again, we go node, and what happens, we add another node inside, but again we have that antinode at the end here. Okay, so you have an antinode. So here we go from then the third to the fifth. And kind of the relationships you can see for the third harmonic, the wavelength we have 3/4 of a wave in here, so the wavelength would be represented by 4/3 of that length. Here you have 1 1/4 wavelength in here, so the wavelength of one wave would be 4/5 L. Alright, and then taking the speed equation, again, speed of sound is going to be constant in that medium. We can then use that relationship to find the frequency, which would be the velocity divided by the wavelength. And here gives us our kind of a relationship between wavelength and frequency for these different harmonics. Okay, so notice we are getting the first harmonic, third, and fifth. So our n values that we're looking at in strings would be 1, 3, and 5. So we're only looking at the odd integers here, not all integers, but just the odd ones. Okay, so here's kind of going through it. Anytime we have a closed end, again, we're getting a node, right? So that's that closed end that it's not allowing to oscillate, so we're always going to get a node at that end. The other end, since it's open, we are always going to get an antinode, okay? Something like that. So it can be any variation between those two. So what we see then is we get this equation, right? Where you get the frequency or the number, the harmonics are equal to NV over 4L, where N this time, and here's the key part, N can only equal 1, 3, 5, 7. So N is basically all the odd integers, not looking at any of the evens, only the odd integers. Right? And again, if you look at it, what causes that? Just because we always have to have a node and an antinode at the two ends, and we have to somehow squeeze the next one in between that node and antinode, making sure we always have a node following an antinode, or vice versa. Okay? So, again, it's kind of the same relationship. These standing waves, again, don't occur at every frequency, but occur at special ones. And again, this n being equal to 1, 3, or 5, our standing waves are going to occur at, so whatever we have is going to occur at some multiple of f1, which is, again, the fundamental. But now our integers are only going to be the odd integers, not the evens. All right, now let's look at tubes open at both ends. So similar to one with closed at one end, we had a node. Here, since we are open to both ends, these particles are free to oscillate, so we're going to have an antinode always at both ends. So we're going to start with two antinodes and a node. Okay, if we compare this to standing waves on a string, right, at standing waves on a string we had two nodes, one antinode. Notice here we had a half a wave. Notice here if you put this together, you have a quarter wave plus a quarter wave, and you are actually getting a half a wave. Okay, so we're going to get, really here, if you think about it, the same relationship we did for standing waves on the string. Okay, the wavelength is going to equal to 2 times L. The third one then, the second harmonic then, we have antinode, antinode, and then we add in another antinode in between, and we get two nodes in between those. Right, so it's kind of going in opposite of what we did for strings. Because with strings we had node, node, and an antinode in between, and what we always tried to do was add in another node. Here we're adding in another antinode. Alright, so we're jumping from the first to the second. Notice here you have quarter of a wave, half a wave, quarter of a wave. Add those together, you get one full wavelength. So within this length of tube, you get an entire wavelength. And going then to the third, it's kind of the same process. So notice here, right, we're jumping from the first to second to the third harmonic. Okay, so this is kind of similar to strings and to standing waves on strings. I'm sorry, and we're getting kind of the same relationships we've seen before. So when the pipe open at both ends, again, I kind of explained how these standing waves occur and how you get that interference pattern. All right, so if we look at it, we said that lambda would equal 2L over n. Right, so plugging this into the wave speed equation, again, the speed is going to be constant in that medium. We get this relationship then for the frequency of the standing waves. And just like standing waves in springs, it's going to be some integer of the fundamental frequency. Right, and now this time our n value is going to be all the integers. Okay, so the key thing to remember here is that between closed and open end, closed end you're only allowing the odd integers, open you're allowing all integers. Okay, so n could be anything. And again, they're always multiples of that fundamental. Here's an example problem of how we can use these problems of interference with sound waves and standing waves. So what we have here, something that you will do in class, is you have a tuning fork that's being held over some sort of tube. right? That's basically placed in water. So what happens here, if you think of this, you have a tube that's open at one end, closed at the other. So this is going to represent a closed tube. So what happens is you're going to vibrate this tuning fork, it's going to oscillate the air particles, and the air particles here are going to travel down the tube until they hit this closed end, bounce back, interfere. And by changing the length, you're going to get varying sounds of intensities that are going to match those harmonics. Okay? Remember the multiple of the fundamental. Alright, so in this problem it says the smallest value of L in which a peak intensity is 9 centimeters. So at this 9 centimeters, so when L is equal to 9 centimeters, that is the smallest length in which you are getting a increase in the intensity of sound. So what this is saying is that at this length, okay, this is where you are getting your first interference of sound. So at length of 9, you are basically getting the fundamental frequency given this tube and those properties in that tuning fork. Okay, again, the fundamental frequency is going to vary depending on the tuning fork we're using, the tubing we're using, and all those other aspects. So in this type of problem, our fundamental is going to be found at 9 centimeters. So first we want to find the fundamental frequency, and then we are going to find the next two resonant frequencies. Okay, so this is a tube closed at one end, and what we should have is that the frequency of that standing wave is equal to NV over 4L. And again, here's where you have to apply, okay, N, remember here for a closed end, is only the odd integers, so 1, 3, 5, and so on. Alright, so right now we're looking for the fundamental. Then asking us for the next two, we're going to be looking for the third and the fifth harmonic. Alright, so looking at the first one, trying to find the fundamental. F1 will equal N, which is 1, V, which if we don't know, we always assume speed of sound in air, 343 divided by 4 times L. Make sure I put this into meters, which would be 0.09 meters. And plugging that in, we're going to get a fundamental frequency of 953 hertz. Okay, so here's the fundamental. Then asking for the next two frequencies, we are not looking for the second and the third, but we are actually looking for the third and the fifth. So we could, yes, go back and plug into this equation. The only thing we don't know is that these are going to occur at different lengths. So how do we find these? Well, we have to know that any standing wave is going to be occurring at some multiple n times the fundamental frequency. So if we know the fundamental, we can easily find the standing waves at the other basically the other harmonics by using just multiplying that n value times the fundamental. So the next two would be 3 times 953 hertz, and then 5 times 953. And you get values of 2,858 hertz for the third, and then 4,765 for the fifth harmonic. Here's kind of a simple problem on how to use standing waves in air columns.